the start of the Cretaceous, but just to, I guess, make the point that that also be split into two different parts. So first of all, to consider the lower Triassic, the latest Triassic up to the Middle Jurassic, when the rifting of Argoland occurred, or the separation of that terrain occurred, and then the plate reorganization that occurred after that, and the events that happened in the Upper Jurassic to the Lowermost Cretaceous, leading up to the separation of Greater India. So this map summarizes nicely the fault patterns that resulted from that period of deformation, and I think some of the important observations, the very strong preferred north-south orientation of a lot of the fault systems. We'll look at the way in which they interacted with the northeast-southwest trending faults formed during the Permian rifting that Sarah has just described, and probably responsible for the localization of the Exmouth and Dampier subbasins, at least on the margins of the Exmouth Plateau. And we'll also look at the way in which that sediment input from the east continues to be very important during this period of time. So to look first of all at the effects of that Permian age drift on the subsequent deformation, and this was work that Amy carried out following her mapping of those Permian fault systems, was then to model the subsequent deformation. So her models involved a rigid cratonic block on essentially the southern end of the margins, from the right-hand side shown here, a large fault which represents that Permian rift filled in with the layers of sediment, which are sort of shown in the brown and yellowy colors in here. So that was the starting state. That template was then subject to extension with different extensional velocities, slow, intermediate, and fast. And then Amy also varied the strength of the lower crust from weaker crust at the top to stronger crust at the base. And I suppose one of the characteristic features of the Northern Carnarvon Basin that I should have pointed out on the previous slide really is the way in which the rifting is concentrated, or the extension is concentrated into those marginal basins on the south. And then there's very distributed pattern of much smaller displacement extensional faults all the way across the very extensive region of the Exmouth Plateau. And it was really these lower models with the highlighted in the red box with the larger lower crustal strength that sort of replicated those geometries most precisely, with the marginal basins forming adjacent to the initial basin bounding faults created in the Permian, and then the distributed set of extensional faults across the rest of the Exmouth Plateau. So with stronger lower crust and intermediate extension velocity. So perhaps indicating that whatever lithosphere was left behind after that Permian rift event over the Exmouth Plateau was relatively strong. So again, this shows some of the regional mapping, also shows the very extensive mapping carried out by Geoscience Australia, by Steve, Nadej, and Claire in particular, which has been a great help as well to be able to integrate that with ours. So this is showing the structure at the top of the Triassic. In other words, after that sort of period of filling the Permian rift, and then the effects of the subsequent Mesozoic deformation. And again, you see the very strong north-south orientation of the faults over large parts of the Exmouth Plateau, the northeast-southwest orientation of the marginal basins reflecting the earlier fault system, and in particular the synclinal nature of the structures in the Dampier subbasin, which perhaps, as shown by Sam in his PhD, reflects reactivation of those Permian faults in a ramp flat geometry, producing those broad synclinal structures. So sorry, maybe I'll just also say the other important thing that Haller, Rohead, O'Brien's work has shown is that that fault activity initiates in the latest Triassic in the Berriasian in the western parts of the Exmouth Plateau, and work from BHP also suggests the same for the Exmouth subbasin. then becomes younger towards the east, occurring in the Lower Jurassic and the Dampier subbasin. Central parts of the Exmouth Plateau are not occurring until the Colovian, when you get over to the eastern parts of the Exmouth Plateau. So there's a migration, just as there's a migration of the Permian rifting into the Triassic from here over to here. That same west to east migration of fault activity appears to occur during the from the latest Triassic into the middle Jurassic. Sediment input at that time, as I say, was predominantly from the east. This is a thickness map created by Peng Chen from, which shows the entire thickness from the base of the Jurassic to the Valanginian unconformity. So it sort of combines those two different events. But the sort of upper Jurassic and Cretaceous sediments are very thin in large areas apart from this southern part of the basin. So it largely reflects the lower and middle Jurassic sediment thicknesses. You can see this depot center in this area here. You can see the thinner sediments lapping onto those early formed fault blocks in this area and completely pinching out into the elevated fault blocks that were present further to the west in the Exmouth Plateau. In this part, on the edge of the depot center, we've got some really nice seismic images showing the presence of what's very clearly a submarine shelf edge with submarine scarps developed at the top of the slope gullies all the way down it, large straight, what are probably mud-filled canyons on the steeper part of the slope, and on the lower slope where the gradient decreases, those systems become meandering and sand-filled, and hence the amplitude contrast that you can clearly see there. So we can fairly clearly associate that depot center perhaps with the edge of that shelf system, and then sediment starvation occurring further over to the west. What's quite interesting is this quite marked change in sediment thickness along this north-south lineament here, and I'm at the moment still to investigate what that might represent. But the other thing to note is that we can also see fluvial systems in sediments of the same age in the Roebuck Basin, which suggests a continuity of the sedimentary systems between the Roebuck Basin and the eastern parts of the Carnarvon Basin, which maybe suggests that the Thuin Graben, the structure that separates those two so-called subbasins, or those separate basins, doesn't necessarily have a lot of expression during the lower and middle Jurassic. Things then change very dramatically as we, after Argoland has separated and the action switches to the western margin, and in particular, the significant sediment input, and in fact, very significant amounts of uplift and erosion that's occurring at the northern end of the Perth Basin and the southern parts of the Exmouth subbasin, feeding sediment into the northern part of the Exmouth subbasin and onto the Exmouth Plateau. And you can see that very clearly. This is just a structure map of the top of the lower barrow group, or the largely Berriasian, a little bit of Valanginian sediments that are present within that. And you can see clearly just from that structure map, the very well-defined shelf edge that we have in the barrow group, showing the Jurassic sediment supply from the east has switched off, and the sediment is now coming from the south. And that continues until breakup occurs. The Valanginian unconformity marks that breakup. But again, what's very interesting is the deformation and the distribution of uplift associated with that unconformity. As you said, a lot of uplift and erosion to the south, producing the barrow group sediments. They're deposited in the Exmouth subbasin, shown in this thick sequence of sediments here. This is what we were showing on the previous map, and this very spectacular angular unconformity that shows the Exmouth subbasin sort of popped up at that when the breakup occurred, but that was actually very, very localized, although it did result, as I say, in this spectacular unconformity that you can see here with a very, very small time gap, just a few million years across that unconformity. Central parts of the Exmouth Plateau are relatively flat, thin sediments, conformable or paraconformable sequences. You don't see any clear evidence of uplift occurring in that part of the area. But then again, when we get now to the flanks of the Thuin Graben, the blocks such as the Emu High pop up and we get these spectacular planation surfaces that may have initiated during after the deposition of the Legendre group, the Middle Jurassic sediments. That Middle Jurassic event may have caused the formation of the Thuin Graben at that time, perhaps, but this clearly remained a high above wave base, presumably to produce this very nice planation surface that you can see in that area. So the distribution of the uplift is very variable. And again, I think that's something that warrants further investigation. What is interesting is that immediately after that uplift, then again, there's another change in the sediment supply direction. The uplifted Exmouth subbasin now supplies the sediment towards the northwest. It's not quite as clear on this map, but again, you can maybe just make out a very subtle shelf edge here, which the interpretation will help you. So the uplifted Exmouth subbasin is now supplying sediment from this area, which sort of forms a much smaller shelf feature here, but interestingly, it sort of spills out around the front of the lower Barrow Delta to deposit its sediments, again, more broadly over the Exmouth Plateau. So that's the sort of end of the rifting story. The breakup has occurred, the ocean crust has been developed all the way around the margin. So we have what is a passive margin that subsequently develops, but perhaps maybe not quite as passive as all that. So I'll hand back to Sarah for the final part of the story.